It is really pleasure for me to introduce stalwart Professor Evie Sampath Kumaran for today's talk. So Professor Evie Sampath Kumaran is a condensed matter physicist and distinguished professor at Tata Institute of Fundamental Research. So let me mention one more thing, that he is one of the senior most faculty in Tata Institute of Fundamental Research, and Professor Sampath Kumaran is known for his research on thermal and transport behavior of magnetic system. He pursued his doctoral degree from University of Mumbai in year 1982 and has gained postdoctoral experience on valence fluctuation as an Alexander Humboldt Fellow at Free University of Berlin. So he chaired Department of Condensed Matter Physics and Material Science in year 2008 to 10. Later, he served as the Dean of Natural Sciences faculty from 2010 to 2013. After 2014, he continued as a distinguished professor in TIFR and had a brief stint as a director of the institute in 2015. He also served as an honorary professor at Jawaharlal Nehru Center for Advanced Scientific Research from 2001 to 2015. He is an elected fellow of all three major Indian science academies like Indian Academy of Sciences, Indian National Science Academy, and National Academy of Science, as well as World Academy of Science. So he also won the award of Santi Swarup Bhatnagar Prize for Science and Technology from Council of Scientific and Industrial Research for his excellent contributions to physical sciences in year 1999. He is a member of editorial board of Solid State Communication, Journal of Magnetism and Magnetic Materials, and Scientific Reports, which is like a journal of a Nature Publishing Group. Professor Evie Sampath Kumaran has supervised many PhD students and postdocs and like few master's students. And he is expert in the field of magnetism, superconductivity, physics of D and F electron system, Kondo lattices, geometrical frustrated magnetism, spin chain magnetism, multiferroics, and nanomagnetism. Now, this short introduction is not sufficient to describe his all the contribution to the science, but given the limitation of time, uh, I will request Professor Kumaran to start his presentation.
Good afternoon. Thank you, Jayavardhan and Kamla, for inviting me for this session. And I'm really very honored by this invitation to give a talk for the Faculty Development Program and the AICTE and organized by SRM. My talk actually is basically on magnetism. I was told that there could be some good number of MSc students and PhD students apart from faculty members not working in this field. Therefore, I would give a 1 hour talk, and therefore I have to keep it at a level that at least some message, there can take home message at the end of my talk. Therefore, I have to keep it as much tutorial as possible, at least in the initial part. Of course, in the second part, I've tried to give some glimpses of some of my own work, a little bit more technical. So the point is here is that this field is a very, very interesting field. Magnetism, as you know, well, this is a very age-old field. Even before human civilization began, people knew how to use magnetism for direction, move from one place to other, things like that. Therefore, this is such a very vast topic. One of the very exciting topics in condensed matter physics. And of course, there is no way that I can talk about everything. And given the nature of the audience, I should try to keep it as simple as possible. And however, I have to assume that people know, their particular students, what is paramagnetism, what is ferromagnetism, what is antiferromagnetism. As many of people know, it will be boring for many faculty members who are listening to my talk, but nevertheless, let me give some brief introduction. When you say para, you have to say that every atom has an unpaired electron. Okay, this unpaired electron at one site interacts with another site, they align the same direction, you call ferromagnetism. They align the opposite direction, they are called antiferromagnetism. Of course, they are much more complex magnetic behavior. Let's not go into the detail. Let me assume that, I mean, people, audience, particularly students, really know about this particular elementary aspects of magnetism. And you know that when you talk about magnetism, the first material that comes to our mind is iron. You know, the ordering temperature is quite high for that. It is a very well-known magnetic material, which is very widely used. And it's less well known is that even 4D electrons and 5D cells like ruthenium, rhodium, palladium, which is 4D element. And then you have 5D elements, even platinum also can exhibit magnetism, which are very well known, actually not often described in MSc textbooks. And what I'm going to talk about is that I'm going to talk about the F electrons. You know, as I already mentioned, that this is already known, and this particular, sorry, I'll switch off the cell. Okay, so this is of 3D elements which are magnetic here, which are very well known. We have 4D here, this is 5D here. And of course, one can keep on giving talks for hours together with magnetism of all these material. Even today, iron magnet is not very well understood. Now, what I'm going to talk about is relatively less recognized magnetism of the 4f electrons. You know, the 4f electrons, when you talk about 4f electron, you're talking about lanthanons. And you can talk about similar concepts are available, applicable also to 5f, for example, actinium. Lanthanons, 4f elements, there are 5f elements. Is a sixth period, this is seventh period. So therefore, I'm going to little bit focus on 5f electron magnetism, 4f electron magnetism. And it's quite interesting to see that this field is basically 5 decades, essentially 5 decades old. There is a lot of history behind it. There are newer concepts that have been developed in condensed matter physics based on the studies of 4f electron system, particularly magnetism. And there are thousands of papers on this 4f electron containing material. And of course, I cannot talk about everything. And there are potential applications for thermoelectric applications, also from the energy angle, also various other for magnetocaloric effect, even from the application point of view. And people are trying to discover materials based on magnetism of 4f. They are going to be very challenging. So therefore, it's of interest to understand. I mean, the reason I want to stress here is that if you look at the MSc textbooks, if you look at it, still such concept not really introduced. That is the purpose of my talk here. That says there are many college, university professors are participating here. It is a good idea to sort of introduce subject, particularly with those people who are not working in this field. Then I'm just going to introduce this subject here. That is, I have very modest aim, try to introduce the concepts with some examples. So what I plan today, I want to give a very brief historical perspective of the 4f electron magnetism. And I would say that even today, the field is still emerging. And there are many things still not understood. I'm going to give a bird's eye view of historical perspective of the 4f electron physics in general, particularly 4f electron magnetism. Okay, so this basically I think, as you know, already I started with the periodic table, which all the BSc, MSc, PhD students know it. And I already defined what is 4f. I'm going to talk about the F elements here, basically mainly the rarest here, which are lanthanum elements starting from lanthanum to lutetium. I must say at this moment, when I say rarest here, we also include scandium and yttrium. But you know, if you look at the chemical properties, also even magnetism wise or superconductivity wise, or many solid-state properties, scandium and yttrium also behave exactly like other rarest. Therefore, for all practical purposes in the literature, scandium and yttrium are really clubbed with other lanthanide system. Okay, what is the difference? Look at this physics of the transition metals in the periodic table. They are mainly governed, particularly magnetism, are governed by 3D, 4D, 5D, and 5f and 4f electrons. So there is a fundamental difference. The difference here, when we come to 3D, look, I'm showing here the 3D here. The radial, where the electron density, radial distribution function, it is just outside the ionic core here. When you come to 5f, they are almost between the ionic core and the valence electron positions, and then they are somewhere in between. It was traditionally believed the 4 of electron is well within the ionic core. If you look at really different function, it's supposed to be sticky local, like that is basically the belief. So these basically the elements I'm going to talk about lanthanum from 57 to 71. There are something like 15 elements. If you look at it, the 4 of orbital, the outermost configuration actually does not change. Basically 5d1, 6s2, the xenon ionic core. The only difference between lanthanum to lutetium is the 4 of electron count keeps changing to move from lanthanum to lutetium. When you come to lanthanum, it is you have no 4 of electron, believed to be no 4 of electron. I would like to understand word. The statement believed to be for a long time there is no 4 of electron lanthanum. In my talk later, I'm going to contradict this statement. Okay, what exactly I will tell you later. But however, historically, it was believed that the 4 of electron count actually is increasing when we come to cerium. Sorry, my error. When cerium 2, you have 1 4 of electron, 2, 3, 4, 5 keeps increasing, keeping the outermost configuration intact. Okay, therefore, historically, valency is defined as a number of 4 of electron. Okay, in the 4 of. If you tell what is the valency of rare earth, you can say what is the number of 4 of 4 of. Okay, for some elements in periodic in this period, another valence state is possible for cerium dioxide, When it's called cerium dioxide, cerium O2, the 4 of electron inside is supposed to be believed to be 0. So again, I'm going to contradict it later. When you just instead of europium, you can europium 3+ state. You have 6 4 of electrons, but europium 2+ has 7 4 of electrons. Similarly, samarium, also ytterbium, and things like that. Therefore, some of the elements have the tendency to exhibit more than one valence state because their other valence state is energetically favorable. This is at the end of the periodic table, beginning of the periodic table, middle of the periodic table. So please keep that in mind. Therefore,
excuse me, sir, you have got muted, sir, somehow.
Sir, you have to unmute your mic.
Sir, kindly unmute yourself. It will be in the bottom left panel. In the bottom panel, if you go, sir, there is video.
Okay, unmute. Yes.
Now it was
I don't know how we got it. Okay, sorry.
Yeah, it is fine, sir. Thank you.
Where is my talk now? It has gone. Your screen sharing is paused. Where is my talk now? I'm opening again.
Yeah.
I'm coming now? It's coming now? Share the screen. Can you share?
Yes, sir. It's visible.
It's visible. Okay, fine.
So, please make it full screen.
Okay, fine. It's clear?
Yes.
I think this. Okay, fine. So what is happening is that we go from cerium to lutetium, you could see a number of electrons only change here. There is no other fundamental difference. And you have a spin quantum number, orbital quantum number, and your total J here, which you can derive from Hund's rule coupling, you can derive from textbook. Then what is called lead G factor. Okay, and then what is the important parameter? The T-John's factor here is given by Gj minus 1 whole square J into J plus 1. That derived knowing the value of L, S, and J. And this is supposed to be maximum for somewhere here, middle of the lanthanons. In other words, this is a very important parameter for rare earths. This will tell you if you know the parameters for gadolinium, for example, magnetic outlet temperature, or paramagnetic unit temperature, or spin disorder contribution. If you know for one element, you can derive what could be the value for the other element. This is basically the concept of the John's factor. Okay, this is supposed to be a normal behavior of rare earths. Okay, so you expected to obey this law, and you will find that many systems disobey this particular law, the scaling out. Now, historically, you could see that when it comes to gadolinium, now this is a radial distribution function of 4F, and these are 5s, 5p with the maximum electron density. Somewhere here, this is the place where the bonding takes place. Somewhere the place where you're bonding between two rare earths, you would find the 4F electron density is actually almost 0 here. Therefore, historically, 5 decades it was believed that 4F orbitals are strictly localized, well within ionic core. So under this assumption, you can say what is the valency of 4? Valency is a measure of 4F occupation number. The 4f was considered to be very deeply localized, very well screened by the 5s and 5p orbitals. This was the original traditional belief 5 decades ago. Okay, so this already said that. Now, therefore, however, this picture breaks down. Please remember that there is a deviation, the sudden realization of that the 4f orbital is not as localized as what people believe, or suddenly realized 5 decades, which I'm going to historical background I'm going to give you now. Now there's the deviation because many phenomena are subsequently discovered, okay, which tells you there's a deviation from this localized picture. What are the phenomena? Of course, one is that they can undergo magnetic ordering, which is nothing to do with the in fact, electrons are localized can undergo magnetic ordering. Now, the phenomenon for balance fluctuation, mixed balance, which is called mixed again.
Sir, actually there is some echo coming in between, sir. I am sorry to request. So mic, can you please bring close to your mouth? I think you are using, sir, this headphone.
Okay, can I remove it? Can you hear me better?
I think it has improved little bit, I would say.
Okay, fine. Let me remove it better.
Okay, sir.
Can you hear me?
Yes.
Can you hear me now? Okay, fine. I removed this microphone. Okay, it's better if it's audible. Okay, so you have various interesting phenomena which one comes across in 4f electron systems, to some extent also 5f, what is called Kondo effect, Evie fermion, itinerant magnetism, spin fluctuations, unconventional superconductivity, giant magnetoresistance, metal-institute transition, spin chain magnetism, and a new concept called magnetic fermions, and things like that. Of course, there are other consequences, nothing to do with the 4f localization or delocalization. Various other phenomena are being described, also geometrically twisted magnetism and multiferroics. There are very unusual aspects of multiferroics which one comes across because of the very unusual behavior of the 4f electrons. What is a phenomenon called 4f localization, delocalization phenomenon. Can you hear me clearly now? Can
yes,
you?
sir. Yeah.
Okay.
I am comfortable.
My focus here,
Yes,
4f localization and delocalization phenomena. That is, they sometimes look like the 4f electrons are deeply localized, sometimes it looks they are delocalized. Okay, now I'm going to give a brief overview of the historical perspective of that. Now, actually, this phenomenon, there are enough indications of this phenomenon even 100 years ago. You know, when in 100 years ago, you know, the famous physicist who discovered actually the father of high pressure physics, the Bridgman. He was studying all the elements in the periodic table under pressure. He took up cerium metal. When he studied cerium metal, he found there is a volume collapse, and by applying pressure or something like 12 kilobar. So then he found that the pressure at which the transition takes place varies from one lot of cerium to another lot of cerium. So he did not understand at that time. Subsequently, there are other groups who actually confirmed, yes, there is a volume collapse of the cerium. So it was left like that. And then 1949, after 30 years, another group by Lawson studied this compound more carefully until they confirmed, yes, there is a volume collapse of cerium by applying pressure of 15 kilobar, and is isostructural. There is no change in the crystal structure. So he was the first one. But you remember, these are 2-page paper in physical UP. Today, there is not even abstract you have. You see, they are not even abstract here. The 2-page. Today, if you send a paper, 2-page paper without any abstract, without any concluding para, it will get rejected immediately. You know it today. Today, you cannot do that. So those days, science was done actually very little bit more informally. Journals are accepting paper informally. This paper is a very casual paper, come to think of it. Read the paper very carefully. 1999 physical review, 1949 paper. So, and then these authors went to Pauling and Zachariah. Sorry. Can you hear me?
Yeah, we can hear. I'll request other participants to please keep your microphone muted.
Yeah. So, okay, and then these authors discussed Pauling and Zacharias. And again, I'm trying to tell you, they didn't take any credit for it. The middle of the paper, they will say, we discussed the Pauling and Zacharias. And they propose idea, since there is structure is not changing, there's a possibility the electron from cerium 4 of shell is going out and participating in the bonding. Okay, and the reason why they propose is that, you know, cerium dioxide. The example is here. Look, cerium dioxide, there is no 4 of electron in the 4 of shell. Okay, fine, it is possible. Therefore, the electron completely has gone out of 4 of. So it was for the first time the concept was proposed. Electron actually can go out of 4 of shell, get knocked off, and occupy the conduction band. So therefore, the idea of valence transition is not when valence transition was proposed by Pauling and Zakariansen in this paper 1949. Okay, and there were other people are trying to study the cerium material, cerium element in detail, and a lot of groups worked on it. And this is a, if you look at the phase diagram of cerium, people studied this phase diagram published 1917 handbook of by Geschneider as a function of temperature and pressure. This is an extremely complex phase diagram of cerium. Can you hear me, all of you? Yeah. Sorry. Okay. Phase diagram of cerium. Can you hear, right? Can you hear me? Yeah. Okay. Look at that temperature, function of temperature and pressure. This is called gamma cerium. It's called alpha cerium. It's very complex. There's structural change in between beta cerium, and that is what is responsible for all the confusions. If they cool the sample and take data here, they get another mix of this one and this one. There is some other disease called first order phase transition problem here. This transition is first order here. This sudden phase transition here. There is another high pressure phase and a very high temperature. There is one more. There is one more phase. There is an extremely complex phase diagram. This is a discontinuous phase transition. This is a continuous phase transition. So therefore, it took 20 years to arrive at the phase diagrams from comparison pressure that to conclude, yes, there is isostructural phase transition, this place to this place. Also, if you vary the temperature, you go from here to here, however, you are going through another phase here. Okay, now, people did not understand what is the origin of the isostructural phase transition. And then 1965, there is a paper by Russian group. This Russian group is doing studying spectroscopy of many materials, electron, the X-ray absorption spectroscopy. This spectrum basically removing 2p electron from the 4 of shell and putting in the conduction band. There is a transition energy, variable ultimate energy. Okay, so they have found that instead of getting one transition energy, you could see here there are 2 transition energies. This particular point you forget. And if you look at the 2 transition energies here, you should have got only one. There is only one side for samarium. Okay, samarium was supposed to be trivalent those days. Therefore, you can expect only one. For one valence, you get only one line. One peak, instead they get 2 peaks. So these are they could not understand. Look, there is only one side for samarium. How is it possible that you get 2 lines here? The X-ray absorption spectroscopy. So they do not understand. They probably felt as sampling inhomogeneous. There's a possibility that some place is 3+, some place is 2+. Then chemical inhomogeneity in the sample. They left it like that. And then the field got advanced, a better understand developed. But you know, and then subsequently the susceptibility was studied by some groups, and you find that also samarium mass bar was studied here. You know, samarium mass bar measures the F electron, the S electron density at the nucleus of the atom you are studying. So the S electron density of the nucleus, basically measured by isomer shift here, plotted here, is a measure of valency of any element you are talking about. The valency is different, isomer shift is different. It refers to some reference material. Okay, in this case, is samarium with reference to samarium trifluoride, which is trivalent. If this material is trivalent, you should get trivalent. You should get isomer shift close to 0. Divalent, you should get somewhere around -1. In this case, they're getting something in between. Remember that neither here nor there, somewhere in between. And the susceptibility also is something in between. That's what you expect for divalency and the trivalency. Of course, this picture is not very clear. It's from what I explained to you. Basically, susceptibility is intermediate. Okay, on top of it, one of the valence states is should be magnetic. Samarium 3+ should be magnetic, whereas samarium 2+ is non-polar magnet, which is not magnetic. This should be magnetic, whereas they found the material is not magnetic. Suppose the foreign electron has lost its magnetism, despite the fact that in this temperature range, you see curious behavior. But there is no magnetism. You follow what I mean? High temperature data shows that there is a magnetism. When you decrease the temperature, you look at susceptible becomes flat here. You look at the dotted line here. There's some small dependence. You note that. It becomes flat as if it becomes polyparamagnet. Polyparamagnet is basically non-magnetic. So susceptibility is intermediate between what you expect from two valence states. High temperature looks as if it is magnetic. At low temperature, it looks as if non-magnetic. There is a transformation from the magnetic state to non-magnetic in the low temperature. So this could not be explained at that time in the late 1960s. Now, field got developed further when the Jayaraman was actually nephew of Sir C.V. Raman, and he from Bell Labs. They studied chalcogenide, samarium sulfide, telluride, samarium sulfide, and he found for samarium sulfide it behaves exactly like cerium metal. When apply pressure, as function of pressure, you could find there's a volume collapse here. Your resistivity drops suddenly at this some pressure, something 6 kilobar, 6.5 kilobar. There's first order transition. There is hysteresis here. However, in come to samarium selene and telluride, you could see the same thing happen, but however, continuously. Here, there is a sudden change in electrical distributivity, huge change in electrical distributivity under pressure. In one case, is sharper. In other cases, it is sort of normal. When they studied the so-called high pressure phase of samarium sulfide or high pressure phase of this material, they behave exactly like cerium in the sense that high temperature you see magnetic susceptibility you see Curie-wise like at low temperature it is non-magnetic. And then actual explanation proposed by 1970 by these two scientists in California, they are the first one proposed the foreign electrons get demagnetized. The high temperature it looks like magnetic. At low temperature, it gets demagnetized because they get delocalized. There are much more concepts like Friedel-Anderson model and things like you don't know about all these things. They proposed the idea there's an intermediate, when the terminology called intermediate valence was coined by this paper. Right? It need not be integral. It need not be 2+, need not be 3+. It can stay in between 2.5, 2.6 and things like that. This is the first term that produced the first time the concept of intermediate valence was coined in 1971 by this author. And there are, of course, theories like samarium sulfide, samarium hexaboride, alpha is called alpha serum high pressure phase. They behave exactly the same way. The idea of intermediate phase because the electrons get delocalized from the core and gets delocalized and comes back to core of shell. It keeps fluctuating between the local orbital and the conduction band. With time, it undergoes even at t is equal to 0. It's called thermal 0-point motion. The term of increment valence, you could see interval coined by the authors here. Okay, now people did spectroscopy. Now people further proved by electron spectroscopy measurement. This is the photoelectron spectroscopy here. You could see if samarium is divalent. Samarium sulfate, samarium divalent and ambient pressure. These are typical fingerprint. There are details here in detail. These are spectrum which you expect if you have single valence state. If it is trivalent, you should get the samarium arsenide, samarium is trivalent. You should get this kind of pattern. When it comes to samarium, okay, by the way, samarium high pressure, whatever is at high pressure can be tuned by chemical doping. Same thing for the put samarium sulfide, put arsenic. If you can mix these two, make the compound. You find that you use fingerprints of both of samarium 2+, samarium 3+, and this also behaves exactly like high pressure phase of cerium or samarium hexaboride and things like that. They will be exactly like this. On top of it, you could find the 4F level is rather close to the Fermi level. In other words, what that means that energetically it is lying at the Fermi level, that the electron can really go to the top of the Fermi level and come back. If it is deeply localized, 4F electron energy will be far away from the Fermi energy. Position will be far away from the Fermi level. Therefore, you cannot expect the electron to go out. Okay. So therefore, in this case, they find they really pin to the Fermi level. So this is how they proved spectroscopically that they have both the valence states. Okay, whereas I already mentioned mass bar showed average, it was lying intermediate. When it comes to spectroscopy here, electron spectroscopy, like both the valence state. The reason is the time scale of fluctuation is intermediate between Mossberg time scale, that is minus 8 seconds, and the electron spectroscopy time scale of minus 50 minus second. Therefore, the valence fluctuation rate or fluctuation time is intermediate between these two time scales. Therefore, one case you are seeing average, another case you are seeing both the valence. Like I take a photo size snapshot going through photograph. Take a photograph, two people standing there, you will take photograph, both the people visible. If some people are moving, and if your camera is slow, they will see the average position. That's what it means here. That is, you would have proved that both the valence states possible. Subsequently, even thulium selenide, also was found to exhibit. What I want is this phenomenon become a disease. It started with cerium, went to samarium, now you find even a thulium found. In other words, wherever two valence states are possible, okay, there's a tendency for the electron to go out of the orbital and come back. Therefore, valency, so-called terminology valency, I'll modify the terminology later. So-called valency, as originally believed, can actually fluctuate, and you can have intermediate valence state for temperatures as function of pressure you can induce. In this case, in ambient pressure, even thulium selenide was also found with that. Interestingly, this compound does undergo magnetic ordering at 3 Kelvin, despite, as already mentioned, loses magnetism. In this case, magnetism was resigned. There are more complications here. Let me not go into the detail, because this is something with the fact that both the valence states can become in principle or independently magnetic. There are more details of that. We will not worry about that. And subsequently, even samarium metal, which is trivalent, basically, the bulk of the material, the samarium is trivalent. You have 6 electrons on the outer shell. You look at the surface, you will find that samarium is divalent. There's surface valence transition. Therefore, the concept of valence transition, okay, one material can atom go from one valence state to the other as a function of doping, as a function of pressure, as a function of temperature, or even nano, go from bulk to surface were realized as early as 1980, 1978 here. You have realized what the 1972 and 88 turned out very hectic period to understand the concept of, or at least understand means by the time you want to convince oneself that the fluctuation or intermediate valence or valence transition possible was not accepted in 1970 to 80. Okay, and there are details, and we have several papers on this published, including one paper seen here. I will not go into the details. There are many technical details available here. I will spend off on this. Now, this is another paper for europium. Also, I will come to that later. Europium is the core level. I already shown you the 4 of valence band. Here, you cannot look at the core level and try. You will see the core level spectroscopy also signatures of both the valence states if there is intermediate valence. Okay, so here is a compound. It could have function of temperature published in physical review of those days. Rapid communication as function of temperature. You could see this is one valence state given to 2 plus another valence state. These are spin off the split thing. There are details of spectroscopy. You can focus only on this here. You will see the European 2 plus state peak, 3 plus state peak. This is actually changing with the temperature here. 300, 750, and this 70%. Huge change temperature. That means that even the varying temperature, both these states, intensities can really change temperature. These are actually discussed by our group here.
Sir, can I interrupt? Actually, there is some change in the voice again. Some echo is coming again, sir. It was very nice in between, but
okay.
Suddenly, yeah. Now again it is appearing better.
Now is better?
Yeah.
Okay, maybe I'd come a little closer probably.
Yeah.
Okay, is better now? Better?
Yes.
Okay.
Yeah.
Okay, fine. So now let me go to a very specific example of tell you. For example, one of the most famous transfer materials is tetragonal compound chlorine chromium to silicon. They are tetragonal series, a layered compound. Let me not go into detail. Those interested, I can discuss later. And plenty of some 300, 400 compounds have been known. We have very thoroughly studied. These are pioneering discoveries are made in this family. Okay, even a lot of work is done in this family here. And describe that we have published a paper in PRL. How do you know that their valence is changing? This is a very beautiful paper we published. See, you know, you don't have to look at even rare earth. Can you hear me now?
Still some echo is coming in between, sir.
Sir, can you please use your microphone?
I will do that.
Let's check.
Yeah.
Can you hear me better now?
Yes, sir. Now it's better.
Yes, sir.
Right?
Yes, sir.
Better.
Yes.
Okay, fine. Okay, fine. Okay. So this is a very beautiful piece of work which you published in PRL, just like that accepted those days, you know, days publishing PRL, even publishing a paper was difficult. Publishing PRL is much more difficult. This is the electric field. In this case, no, you look at not at the element like europium, which is fluctuating here, which is basically a system where, as I already mentioned, electron goes out and comes back. Okay. How do you prove the electron really goes out? The way we have proved is that you look at another element in the lattice, measure electric field gradient. You know, the valency changes, charge state changes, then electric field also changes. You look at copper element, do copper NMR, and then try to study the electric field gradient at that side, which is a measure of, which is plotted here, which is as function of rare earth. You could see here, if the rare earth valence is 3+, these are two families, silicon and germanium here. Valence is stable, electrical gradient value could be somewhere, should be this much. When it is fluctuating, you could see here, intermediate. You got value is dipping here, okay? And then as function of temperature, you could see here, this is very, forget about these figures. I mean, you could see that as a function of temperature, very huge change in the electrical gradient here. If it is stable valent, this is what you should get here. Almost constant value here, very small temperature dependence because of a lattice effect. There's a huge variation here, and you can derive the valency value from here in principle. An approximate value, you could see European valency is going from almost 3+, almost 3 at low temperature, to almost 2+ at high temperatures. You could see a very huge variation here. So this is the way we have proved that actually charge state is changing in this material. Okay, this is again X-ray absorption spectroscopy. You like electron, photoelectron spectroscopy, the X-ray absorption spectroscopy core level is more bulk sensitive. People, one of the very first papers in this field which we published, that if you have two valence states, you could see that you see two peaks here. Okay, if you have one valence state, one peak here, you can derive this from the valency value from decomposing these curves here. Okay, so this technique was considered to be very ideal technique even compared to electron spectroscopy because it is more bulk sensitive, it is less surface sensitive. So on that basis, I mean, it was assumed people are really using X-ray absorption spectroscopy to understand the valence fluctuation on intermediate valence in this material. Now, this figure I want to show you, this is one of the compound. If you look at anybody reading literature now, we presented, we published our group is the one which is discovered. European palladium to silicon to considered the most exotic material even today, even to the current literature. Look at Japanese, even now people are studying the material. The reason is the following thing. I already shown you one example of European copper silicon, which actually was the first material of europium with the valence change discovered by Israeli group. The second material is European palladium to silicon, which I shown here. As a function of temperature, you could see a very huge change in isomer shift of europium. It's a very sharp change. You could say such a sharp change was never observed before. Even today, no material was found to exhibit such a sharp change in the valency. By the isomer shift is a measure of the valency here. What I plotted is isomer shift measured by mass bar. We can treat it as a valency. Here, this is 3+ state, this is a 2+ state, very huge valency. We discovered another material where you see the weaker valence, weaker change, which still remains intermediate valent, even at low temperature. In this case, it goes almost 2+, almost 3+. It never reaches complete integral valence. It reaches fractional even at this temperature. Here remains truly fractional, complete intermediate. You know, some of the very unique systems which people in the field even now study even after 4 decades. And look at susceptibility, it's a very huge change, the peak here. Because you're going almost 2 places with a magnetic, almost 3 plus which is non-magnetic. This is due to impurity here. This is one of the most exotic papers which I published, which is very well cited. So what I want to say is that, I mean, we have made a very poignant contribution when the people were trying to discover materials exhibiting valence fluctuation. Okay.
This one aspect, and then people were studying, trying to study large number of materials, trying to discover materials exhibiting valence flux. Can you hear me now clearly? Better?
Yeah.
Yes, sir. Yes.
Yeah, it is very clear, sir. Thank you.
Okay. Now, when people are studying many materials, they studied cerium aluminum 3 by this paper published in Solid Communication. One of the pioneering work. This is the landmark in this field. I already shown you one. I showed one more landmark. I will show you some paper, another landmark. And when cerium aluminum 3 is supposed to be trivalent, and you find, if you look at high temperature, look at paramagnetic Curie temperature, it is quite huge. That means it should order magnetically at low temperature. It doesn't order magnetically at low temperature, but instead, you look at heat capacity, very, very huge. If you look at gamma value, electronic coefficient, you look at 1620 millijoules, 1.6 kilojoule, very huge. When you come to copper, it is less than 1 millijoule. It should behave like copper. It doesn't behave like copper. So therefore it was very huge value. It looked very heavy. When gamma is large, means effective mass is large. Therefore, the term heavy fermion was considered by this particular paper because look at effective mass is very huge in this case. It's a very hallmark paper. Look at electron, look at the linear term, very huge. This is due to impurity, ignore that. Okay, and also there are very other interesting anomalies here. Look at resistivity. There is a look at the, resistivity, probably people in the field will know better, that resistivity varies like T square for any metallic system, technically, ideally, okay, called Fermi liquids. So there's a coefficient, T square coefficient, which is supposed to be very extremely small, in this case, very huge. So this was the T square coefficient, heat capacity, and all susceptibility, as I told you here, it is very huge at low temperature. It should be somewhere very low, very small. It's very non-magnetic, but the values which you get is large. So these three terms like T square coefficient, susceptibility, and heat capacity are supposed to scale among themselves. Yeah, they are scaling, but the values are large. Okay, so this is the paper that led to the idea of the heaviness. C is equal to gamma T. Heat capacity is equal to gamma multiplied by T. Gamma is a heat capacity coefficient, which is a measure of density of state at the Fermi level. Therefore, density of state is very large here. Therefore, the system is very heavy. Therefore, the terminology was coined, and people are studying more material. And another material, cerium copper to silicon 2, was studied, behaved like exactly like cerium aluminum 3, published papers 1979 in Physics B. That journal vanished today. The high TC superconductivity was first published in this journal, 1986. All of you know that. Now this journal vanished, and it was recoined. The new name, another name called European Physical Journal. Okay, this particular paper, very prestigious journal those days for Germans, and these authors found another interesting feature. Cerium copper to silicon 2, effective mass was large, heat capacity was low temperature, doesn't order magnetically, though it's supposed to order magnetically. Despite that, it is prepared some 30-40 materials, few materials exhibited superconductivity. That was again further surprising, because you expect cerium, historically, there are another 2 hours talk on that. When you have huge magnetic moment, you are not supposed to get superconductivity. Okay, magnetism and superconductivity are supposed to be antagonistic, at least those days. Now many things are accepted for various reasons. So this material was found to be superconducting at 0.5 Kelvin. So therefore, these authors made a footnote in the paper because they did not find superconductivity in this material. They made a footnote. Some material exhibits superconductivity, and they thought it due to some impurity. However, this author Steglitz, whom all of you know today, is a very well-known scientist. In Dresden, he pursued the matter, and he published a paper, sent a paper to PRL. He studied several materials, and indeed confirmed the presence of superconductivity in a large number of samples, but absent in many other samples. And in fact, they say in the PRL paper that they find only in some 50% of some samples, not in all samples. Today, if you send the paper like PRL, immediately get rejected. Therefore, PRL really rejected the paper. It has difficulties in publishing. The problem here is the heat capacity jump at the superconductivity is huge. In superconducting transition, you do not expect a huge jump. You should scale like gamma, only normal metals. So therefore, since the jump was huge, the referee apparently rejected, saying it is due to magnetism, it is not due to superconductivity. So therefore, this tussle was going on. This paper is difficult getting published, and finally managed to publish, and people subsequently confirmed, yes, it is coming from magnetic flow of electrons. Then it was for the first time recognized that magnetism, superconductivity is coming from the exactly same electrons which are responsible for magnetism. In fact, so magnetism is aiding superconductivity. Earlier it was thought magnetism cannot support superconductivity. This is probably the first paper which has brought out the idea that magnetism can support superconductivity. And of course, there are further experiments, many more materials subsequently found in which similar features were seen and is considered to be unconventional superconductivity. And there are some arguments coming from S-wave superconductivity. There are more details of that, P-wave superconductivity, D-wave superconductivity, due to spin fluctuation, things like that. I will not go into the detail. So this is again a landmark paper which opened up a field called Evie fermion and Evie fermion superconductivity. I hope I'm able to convey the message. And okay, so when therefore people started looking for other cerium materials where you can find superconductivity, where other cerium materials where you can talk about valence fluctuation, valence transition, and they came across a problem that there's a lot of inconsistencies. For example, even cerium dioxide, you know that cerium dioxide, if chemists will not believe, chemists all think, including physicists, that in cerium is tetravalent. That means there is no 4f electron in the cerium. But if you do a spectroscopy by the techniques which are being employed to study the valence transition, that is photometric spectroscopy, X-ray absorption spectroscopy, and people studied, okay, why not look at other insulating materials, also other metallic materials which are considered to be not magnetic. See, ruthenium-2, it was believed there is no 4f electron. Cerium oxide, believed there are no 4f electron. But even in these materials, people found that they behave like mixed valence, they behave like intermediate valence system. You know what I mean? They behave like high pressure cerium, they behave like semi-hexaboride, they behave like cerium aluminum-3. There's a big mess that how come cerium dioxide can, where everybody believes cerium is tetravalent, there are no 4f electron. Even in this case, you find the mixture of both the valence states. There's a big confusion. People thought due to some impurities, and people resolved they're not due to impurities. Okay, so where from it is coming? Therefore, people did not believe the techniques which are being used, like X-ray spectroscopy, spectroscopy, did not believe those techniques. And then actually this confusion led to better understanding of the 4f electrons, and people realized that it is something to do with the tendency of the 4f electron to participate in the chemical bonding. I already mentioned right in the beginning, the 4f electrons are supposed to be localized. Okay, but it was realized not only 4f electron can get delocalized completely, that they can remain localized, they give a feeling localized. On the other hand, the spatial extension can be a little bit larger, they can participate in chemical bonding also. So therefore, and then it depends on that the whole idea of valency gets in the mess, because valency was considered to be a definition of number of 4f electrons in the 4f shell. In this case, you are saying 4f is participating in bonding, something lying core like, something like participating bonding. What do you mean valency? Therefore, people started thinking the valency has to be, the definition of valency should be changed when it comes to rare earths. And therefore, the reason is, if you look at the conventional wisdom, cerium valency never exceeds 3.3, and people did a lot of bench calculation and tried to study the other, using other spectroscopy techniques. I will not get time to go into the detail, like Bremsstrahlung spectroscopy, inverted photoelectron spectroscopy, and the people found that indeed that the 4f electron, you do have 4f electron even cerium dioxide. Okay, the very important, that's going textbooks. Cerium has, for dioxide, cerium dioxide, there is 4f electron. But the problem here is that 4f electron is not with cerium. It is sitting with oxygen. Let's put in simple words. There is a very strong bonding between cerium and oxygen. Therefore, the electrons of cerium, they are sitting in oxygen band. They are cerium character. They also have oxygen 2p character. There is basically covalent mixing. Therefore, they're called extended 4f electron. The concept of extended 4f electron was coined in early 1980. It was confirmed by 4 electron spectroscopy, and then for the other spectroscopies, as well, many spectroscopy techniques. We have published paper also in PRL. Many techniques, also calculations and theories came out and agreed. Yes, you're talking about two kinds of electrons. Some electrons can, with such a large rate extension, sometimes behave like localized, sometimes extended, sometimes can participate behave like covalent bonding. It was believed it cannot participate in bonding. Now it has accepted it can participate in covalent bonding, and therefore you can have 4f character even in the case of cerium dioxide. And if you simply count the number of electron in the 4f shell, you have to define what exactly you mean. Are you talking about localized 4f electron or extended 4f electron or a band like 4f electron? You are depending, but therefore define what you mean by. If I say that number of 4f electron, if I define valency, the number of localized 4f electron, yes, in cerium dioxide you can call it tetravalent. However, if you say number of 4f electron irrespective of where it goes, then cerium dioxide you should call is that fractional occupation. Then it's not fluctuating. Therefore, the concept which you use cerium dioxide is not the same as for other cerium, other fluctuating system. In other materials, we are not about covalent. There's a fluctuation. Here, cerium dioxide is not a fluctuation. There's a covalent mixing. So it's a very important subtle difference which you have to remember. And when you talk about the material, okay. So there are details and there are many techniques. Now I don't have time. These confirmed by spectroscopy techniques by us. Okay. Now let me skip. Now the point which I want to stress is that it is now recognized that now established for the first time. There are papers in 84, 85, 86. Even now papers are coming. We all published some papers that the disease of some tendency to participate in covalent bonding by 4f is a disease. I call it disease or delocalization. It exists also by praseodymium and neodymium. It was believed that praseodymium and neodymium cannot exist. You cannot have the problem. But exhibits even in the case of problem exists. That means the 4f doesn't get localized suddenly at cerium or something. It is a slow process. When it comes to lanthanum, by the way, I forgot to mention, even in the case of lanthanum trioxide, where you don't expect 4f electron, you do a 4f character when you look at oxygen band in the lanthanum oxide. Okay, therefore, if you can always call cerium called fractional valent if you want, but you don't call by conventional wisdom. So therefore, you have to understand what exactly we are talking about. Where is a 4f electron sitting? Depending upon that, the terminology is different. And now, even in the case of praseodymium and neodymium, that you do have some tendency for electron participate in chemical bonding. These come out of many spectroscopy techniques around 9. Now it is accepted. Even papers are coming out on that. So let me skip all these things, and we find that this problem. Okay, there are another paper in PRL that even europium you can have this kind of situations of covalent mixing. Let me skip that. Now, let me go to another important. I have 15 minutes time. I have to finish quickly. That when you talk about magnetic ordering, I talk about two important interactions. I mean, there are many interactions. Let me skip two. When you talk about a simple rare earth or simple metal, the interaction that covers magnetic ordering is called indirect exchange interaction. That's called TRKKY. By these oscillators, the one, for example, 4f here or local moment here can polarize the conduction band. I mean, that here the electron get polarized, the strength is strong here. As you go away from rare earth, it gets weaker and weaker here. But there's an oscillation of 4f polarization. In other words, up down slowly like a wave. The 4f conduction electrons get polarized. Okay, by the local 4f electron sitting, any local moment sitting. That is basically the mechanism of magnetic ordering in any metal. The very important interaction. In other words, if one local moment is sitting here, another local moment here, these two can be antiferromagnetic because here the opposite the conduction band is opposite here. It's a very important interaction. It's called TRKKY. This goes like square of the exchange interaction with the interaction strength between the local moment and the conduction band. Conduction electron goes like gamma square. Now that is another interaction. This promotes magnetic ordering. There is another interaction of a Kondo interaction, which is trying to suppress magnetism. That is a local moment at this site can be antiferromagnetic. Here it is ferromagnetic interaction. Here it can have antiferromagnetic interaction. It's called Kondo interaction. This interaction is trying to suppress magnetism. There is a competition between the two interactions. The one interaction trying to promote ordering because of the oscillatory nature of the conditional electron polarization. Another interaction is trying to suppress magnetism because the tendency at the on-site interaction to promote non-magnetism. So this interaction goes like exponentially with the same exchange interaction strength. One is trying to become square-like, other like exchange interaction. There's a competition between the on-site Kondo interaction with different Kondo temperature. This is archic temperature. Therefore, when you have a single site, yes, it's a single atom or single cerium, you have only this interaction. When you have a number of cerium atoms, a number of rare earth atoms in a lattice, for example, then you can have this interaction. These two interact, single ion interaction and the lattice interaction can compete, can make the situation complex. Now, what is Kondo interaction? You know, they are first actually observed for very small doping of iron and copper. If you look at resistivity, it goes logarithmically with the decreasing temperature here. When you come to copper, you could see here, this goes like positive, this temperature equivalent of resistivity is positive. This is for copper metal. This is electrical resistivity. At low temperature, upturn here. This is signature of Kondo effect here for copper. But however, you can expect Kondo effect for D band metals because for D band is so broad. You put another Kondo ion, you get overlap, the Kondo effect vanishes. Therefore, the people did not tend to believe that Kondo effect is possible in rare earths because the 4F is supposed to be localized. So therefore, the understanding or the discovery of many materials with properties mimicking this behavior, that even in rare earths, okay, behave like a logarithmic variation of resistivity with temperature, proved that yes, basically Kondo interaction. Kondo is nothing but, by the way, I don't want detail again, the covalent interaction. This kind of interaction can be present in the lattice. That is why called the system, valence fluctuation system, or also called Kondo lattices. They are also called Kondo lattices because the electron density at the Fermi level increases and they give rise to the ring. How does electron density decreases? As I already mentioned, every site you have a Kondo interaction. These are cerium, one cerium, another cerium, things like that. Every site you have these antiferromagnetic interaction. Therefore, this antiferromagnetic, the collection of antiferromagnetic sites, okay, at on-site interaction, these renormalizes density of at the Fermi level. Here, there you have a peak signal developing. This coming from 4F hybridization. Is a 4F density here. Normally, you have S electron density of 4F density here. Therefore, therefore, your density goes up, the effective mass goes up. Therefore, the gamma goes up. Gamma is electron. This is the heat capacity linear term. Therefore, this is the origin of the large effective mass of the Kondo lattices. That they are called heavy Fermi, they are heaviness. They are called Kondo lattices because at every side of Kondo ion, they are called heavy fermion because the effective mass has gone up because of enhancement of the density of states. There are already terminologies. And they also expect the Kondo Fermi electron behavior, they exactly behave like any other metal. That gamma T, gamma, except this term is enhanced. A, gamma, and chi are enhanced at low temperature. They scale with each other. They are called Fermi liquid behavior. It's called Fermi liquid behavior. The scaling of these the terms called Fermi liquids. Okay. So there are other things. Okay. Now, as I already mentioned, the on-site Kondo interaction, which goes like exponentially with the local interaction, competes with the intersite interaction, which is RKKY. Okay, if you collect a large number of cerium ions or europium ions, they compete, then your competition between these two can give rise to a lot of problems here. Okay, and at the same time behave like this. Let me skip this, not important. So okay, you can So then your competition between Kondo effect and magnetic ordering. So one tendency, as I told you, is trying to one tendency, see, one interactor we are trying to increase magnetic ordering, which goes like this. This one, magnetic ordering temperature is going up like this. Another interaction is trying to kill magnetism. These two interactions compete, and net result is that if you tune the interaction by applying pressure or by chemical doping or even changing magnetic field, there is a competition between these two. They're beyond certain critical point of the concentration or pressure, you will find that you lose this magnetism. You remember, this comes down at this point here, and you have only this non-magnetic interaction dominates. Therefore, for example, that is why cerium metal or in many materials, you start with the magnetic material, apply pressure or change concentration, you go through the peak of magnetic ion temperature and suddenly comes down. At this point, lose magnetism, and you find you call ferromiliquid behavior. In this region, you see a strong valence transition. Here you have weak valence transition or no valence transition here. Okay, so therefore, what is now discovered is, and there are plenty of very exotic features. Okay, in this phase diagram, this is one of the, I just want to inform you today what people are doing is playing around with this phase diagram. Depending on the material which you choose, many exotic anomalies are found. Okay, and one doesn't expect ferromagnetism here, because ferromagnetism try to kill ferromagnetism when it's trying to kill the antiferromagnetic coupling being kill the magnetic field or even internal ferromagnetism. Therefore, it was believed that ferromagnetism cannot survive in the presence of Kondo effect. And we found many ferromagnetic material which is trying to suppress the Kondo effect. There are many complex variations. We found many material in that. So now what is being, 2000, around 1995, it was discovered the most exotic as of today region is this, where you are about to lose magnetism as function of pressure or function of doping, and you have a complete breakdown of normal metallic behavior. In other words, the ferromiliquid behavior is called non-ferromiliquid. The ferromiliquid behavior which you expect for normal metal breakdown, and there are many theories, many explanations are coming out, many metals discovered. There are many interesting features, including superconductivity, are discovered in this region, and there are a lot of attempts in the current literature to understand, to systematically follow this. Therefore, the most exotic region as of today is the region where there is a critical point where there is a loss of magnetism or non-ferromiliquid. The complete breakdown, the loss of ferromiliquid happens in this region. And I will not go into the details here. And these are pioneering work. By the same thing can be said about uranium. For the first time discovered uranium, breakdown or ferromiliquid or conventional metallic behavior in this material, in the uranium-based material, which are subsequently found in the cerium-based or other European-based materials. Today, we find many exotic anomalies, which in the known literature, ferromagnetic Kondo lattice, non-ferromiliquid, and there are also controversies of what is happening to 4f electron when you vary the pressure. Where is it going? Where is it going? Is it coming inside this 4f or still look itinerant, or transition happening slowly, localized to itinerant as a function of temperature or pressure, happening slowly or continuously, and whether it become, some of the material also become insulating like behavior. I will show you some example. So there is no systematic understanding today. What is happening? Isn't it systematic? There is no systematic theory to completely understand all the varying behaviors of the 4f electrons. One question which I will not go into the detail is that this one picture I show you, temperature as function of the interaction strength between the local 4f electron, conduction band, as I told you, exchange interaction strength, is that where the 4f electron, this is a critical point I already mentioned, that whether the Kondo effect still persists, as I told you, this is a Kondo interaction which is persists in this magnetic Lorentz region or suppressed here. Okay, and there are a lot of controversies on that, and we have done a lot of work to establish one system, which I will not have time to discuss that, through collaboration with Collaborator and MIT spectroscopic techniques, using very powerful spectroscopic technique of measuring low temperature, to say that yes, it is indeed possible that this interaction, which is responsible to kill magnetism, can in principle survive even in this region also. You know, you may say the contradiction. On the one hand, I am saying the magnetism here, on the other hand, the magnetism interaction survives. By that we mean trying to get him weakened. I mean, these are all very complex concepts to imagine. There are theoretical attempts to understand, because the reason is you see the features of the Kondo effect. By that we mean there's a delocalization of 4f electron. Instead of remaining completely localized, it remains delocalized. It tries to become itinerant. By the itinerant is another terminology to understand delocalization. Okay, so therefore you see the features, put in simple words, the region where you are supposed to see localization of 4f electron, which should lead to magnetism, you also see the tendency for delocalization here. If you look at the experimental features. So in some system, you don't find it here. I mean, what I want is varies from system to system. That's called SD wave, spin density wave picture, and the local moment picture. There are two different pictures. Okay. So they're all very, I will not go into detail from cerium, rhodium to silicon 2, silicon 3, which from our own work, you could say magnetic order is a relative resistive as function of temperature. This magnetic resistive magnet, the drop is due to magnetic ordering. You could see by applying pressure on this, you could go from this feature to this feature. For intermediate pressure, you could say expanded form here. This is a linear behavior. At high pressure, you could say quadratic behavior. You know, quadratic behavior, as I mentioned, is a fermi-liquid behavior, conventional metallic behavior. You don't see quadratic behavior, instead it's a linear behavior. So we are going from a magnetic region ordering to a non-fermic region to a fermic region. Then what we are able to slowly even the same material, you can go from one localized picture to a delocalized picture by varying pressure, and we have done spectroscopic measurements, which I will not go into detail, to show that yes, indeed, even in the magnetic organism, you can see signatures of these features. Okay, so let me give one example where very funny anomaly that some of the materials, again from our own work, which actually ours is not the first work, the Japanese group on cerium nickel tin, that they also exhibit insulating behavior. Look at the funny behavior. Look at lanthanum, lutetium, and yttrium. You see metallic behavior of resistivity as a function of temperature. I'm sorry, there's a red line coming. I don't know where from it is coming. So anyway, sorry for that. So then, and then if you look at cerium here, look at this. Temperature coefficient of resistivity is negative here. It's a very distinctly different behavior compared to other materials in this family. Okay, and then we have established, for example, we did tunneling experiment, other thing. You could see there's a dip in the, you look at the density of state that is Fermi level as a function of photon energy. There's a dip here. It's called pseudo gap. This pseudo gap, dip, is responsible for the negative temperature coefficient of resistivity. They're all very exotic thing. Today, one is trying to understand what is the origin of the insulating behavior in this when you talk about in this material, because there are theories which suggest the hybrid is called hybridization gap. The 4f electron, when participates in bonding under favorable circumstances, it can create a pseudo gap. Like you talk about high temperature superconductors, you can also have pseudo gap. That gap is responsible for the negative temperature resistivity. And interestingly, these are the materials where you see also a large thermo power. It is hoped that such materials, which if can be tuned, they can be used for thermoelectric application. This is very important for from energy angle. Okay, so the same material for we applied pressure, you could see there's a change in the temperature coefficient. This is a zero pressure or no external pressure. Under pressure, you could there's a change in the feature. Here, it completely becomes a positive temperature. You know, you can go from this region to region under pressure. And also going through a very interesting intermediate feature, you could say linear behavior resistivity. In this region, you could see quadratic. Here you see a linear behavior. It's a non-Fermi liquid behavior again. So therefore, you start with almost a pseudo-like insulating material, going to a non-Fermi liquid, and finally ending with a Fermi liquid feature. Very exotic features here of lead current. Now, the another material which you discovered, cerium ruthenium tin 6, which is attracting a lot of attention in the literature, is that the same way. So, in the same way that when it comes to cerium ruthenium tin 6, we are attracting a lot of in the current literature, negative temperature resistivity. When it comes to yttrium, lutetium, and gadolinium, you find the positive temperature of resistivity here. They are very completely different behavior. This is attracting from another angle in current literature for what is called topological insulators. Okay, you know, by that I mean that the bulk is like insulating, at the surface it looks like metallic. So this is attracting a lot of attention in current literature. I mean, like semi-exoboride, by the way, is which I mentioned 50 years ago. People study, even today people are studying. These are some of the materials which are due to 4f hybridization gives rise to anomalous properties, anomalous phenomena called topological insulators, continue to attract a lot of attention. Okay, now I don't want to go into the details. And I'll give, my time is up, I'll take few minutes to show even the so-called normal rarers, normal which people traditionally believed, which are normal rarers, they also show anomaly. In fact, that work has come out from our own work. We are first going to point out, study normal materials, normal rare materials, to show that sometimes they behave like abnormal material, as if 4 electrons are localized or delocalized. But in reality, 4 electrons are not delocalized. They remain localized, but they look like delocalized. It's a very funny phenomenon. The new concept is evolving. There are papers in PRL recently, I will show you that. The new concept, a new magnetism concept has evolved. So I just want to tell you. Normally, for example, if you look at plot electrical distribution from temperature, a normal material should show positive temperature equivalent of resistivity, and then the magnetic ordinate should be a drop here. Okay, this is a normal material. Okay, this is what you should see. I will not go into detail for seed gadolinium compound silicon to the experimental data. This is a paramagnetic behavior, and there's a drop at the antiferromagnetic transition here. So, some materials which we reported 2 decades ago, there is a magnetic ordering here, there is a minimum here. I already mentioned the minimum signature of Kondo effect. The minimum signature again delocalized 4f electron. In this case, it is not coming from delocalization of 4f electrons. This was not understood. We have found out again half a dozen materials, reported half a dozen materials. We have papers also in PR to show even such a normal system where you don't expect any delocalization of 4f delocalization. The experimental data shows as if it is delocalized, as if it is a Kondo, but they are not coming from Kondo effect. This is coming from which were not, this concept was not completely understood till recently. There is a paper in PRL. Okay, there are other materials that we have paper in PRL. If you look at even samarium, gadolinium, and they are also minimum here. Then upturn before the magnetic order. This is completely unexpected. So therefore, 4f electron is throwing up a lot of challenges. And there is a paper, paper in PRL recently by American group, 2016. Now there are 2 more papers that come out. They come out with a novel concept. By that I mean that these are all frustrated lattices. In other words, when the rare earth ions sitting on triangular lattice and the antiferromagnetic coupled, they give rise to some extra scattering in metallic situation that can give rise to an upturn. This is very substance of this paper. So the new concept is evolving that Kondo effect, which is traditionally known to give us resistivity minimum, is not the only concept which can give rise to resistivity minimum. There are other concepts, even a simple material can give rise to the extra contribution to resistivity coming from 4f electrons, not necessarily from the delocalization phenomenon. So you could see that the more studying of even simple rare earth materials giving rise to a lot of challenges, giving rise to new concepts. And I just want to tell you there's a paper recently in Science, the material which I found just now, the another phenomenon called skyrmions was found out in Japanese group, and there are certain experimental features like typical Hall effect. You see, these are typical Hall effect features. Only experts can understand better. We plot Hall waves as a function of magnetic field. There's a maximum here. The same data we published 2 decades ago. These are typical signature of skyrmion behavior. Basically, you see a spin, we call spin textures. You could see a very funny textures or orientation of spin, So they're called skyrmions, a new concept in magnetism, which is evolving now, and there are potential applications for next generation information storage. So this material is considered to be, the 4f electrons are considered to be an example for skyrmion, and we report even 2 decades ago, even before the phenomenon was discovered. That time we did not understand. Of course, the group doesn't give credit to us, that doesn't matter, but we are happy to see that the same feature was reported by us 2 decades ago. By look at the feature here. I mean, 2 decades ago in physical B. Okay, we clearly say this completely disobeys all the laws in solid state physics. We reported, we left it. Now today, people are understanding the origin of that. Anyway, so I just want to tell you that the 4f electrons have been throwing a lot of challenges, mainly because of the tendency to exhibit delocalization and localization phenomenon. Sometimes look like delocalized, sometimes locally localized. And understanding is still evolving. It's not completely understood. And more materials you study, it's throwing more challenges. It continues one of very active topics, both theoretically and experimentally in condensed matter physics. And even those systems, 4f systems, which are supposed to be normal, They are also throwing challenges. That is the main contribution of our work during the last 1 decade. Some 4 theses has come out of that work. We have brought out many normal materials. In fact, I don't have time to describe all these. Many new concepts are evolved. And the real challenge in condensed matter theory to understand the physics behind these materials. Therefore, I would say the future really lies, therefore, to study new materials. This is a materials-driven field. I mean, but only thing you have to do a good sample characterization. We should not ignore polycrystal. All this study began with polycrystals. Then you have to study single crystals. I mean, you don't ignore disorder. Disorder sometimes helps you to evolve new physics. Sometimes it kills the real features. You have to augment. Thin film studies are completely open. Heterostructure studies, you can do a lot. Very little has been done. We have done some work on nano forms, very crude way by pulverizing material, but that is not the right way to do it. You have to do heterostructure, is completely open. And there are, if you persist carefully, there are many accidental discoveries. You have to go to low temperature, high pressure, high magnetic field. You have to apply several spectroscopy technique, and you get a lot of theoretical support. And this, my feeling is that it will eventually be a key for many applications, particularly for the energy related issues, power generation, magnetic refrigeration, magnetic recording, and also permanent magnets. I mean, there are a lot of things that could be done. The future is still open, field is still active. And I would like to thank for your passion. I'm sorry I took 10 minutes extra. Thanks a lot for this opportunity to talk to you. Nice seeing you all. Thank you.
Yeah. Thank you, Professor Sampath Kumaran, for giving really amazing talk and mesmerizing talk, I would say. So I am sure most of us must have enjoyed listening and starting from history, then talking about very fundamental aspects of magnetism, then talking about RKKY interaction, Kondo interaction, and then giving the perspective and relating your work to the latest skyrmionics has really been really wonderful to hear all through in 1 hour, you can time say.
This is a very bird's eye view. I'm
Yeah.
sorry, there are many exotic
Yeah,
discovery. It is a very landmark discovery I pointed out.
yeah.
And
So
a
now,
lot of
if
infantry
you
talking
allow,
about it. Yeah. Any
yeah,
questions?
yeah. So if you allow, can I ask request participant to ask questions? So I think now, if any participant is interested to ask question, you are welcome to ask question to Professor Sampath. There is a feature of raising hand in Zoom. If anyone is interested, you may raise your hand and then we can take up the questions.
Maybe my talk is not understandable.
No, I think participants, you can, I have few questions.
Sure, okay. Go ahead. Yeah, sure. Okay.
So any other participants? Okay, if you allow, can
No,
I?
sir. It's nice to hear you. You have covered a lot of things, and you explained Kundo and RKK by interaction, and you have shown very interesting measurement. You have shown how the resistivity is changing under pressure, sir. So we have enjoyed your whole talk. It is not.
Thank you.
So, sir, I want to ask one question in TIFR.
Yeah.
How much pressure we can apply during this magnetic measurement?
Okay, this pressure we can do up to magnetic susceptibility up to something like 15 kilobar, and the resistivity you can do measure. In principle, you can do higher pressures. By the way, I am not with the TIFR Colaba now. I formally retired from TIFR. I am with UGC DAE Center and the Emeritus Professor, also associated with the Oimba Science Center as a JC Bose Fellow right now. So I formally left. Therefore, I can measure nothing there unless somebody is. So anyway, TIFR in principle, Karthik is a man who measured, and he measures around can go up to 80 kilobar resistivity, no problem in that. In principle, provided PPM is available plus helium is available. Right now, because of COVID, you can measure nothing. So anyway, the data which I shown you, I went to Japan, I took data and measured that. We have published quite a good number of papers. We have published quite a good number of papers with the data measured in TIFR also. And I have not covered any of those things here.
So there is a question from a participant.
Yeah.
Is there any applications for paramedical and health field?
Okay, this is something very interesting application from the the permanent magnets, semi-exoboride, semi-cobalt, the sulfide. There are many permanent magnet applications out there. There no doubt, and there are a lot of efforts to the GD5SI4 was one with exotically one of the most exotic magnetocaloric effect system. And there are a lot of efforts for the first 10 years to explore this simple error like gadolinium system at the first order transition to raise the magnetocaloric capacity. And I think gadolinium is metal, simple it's metal is being tried room temperature, but I don't see really worthwhile material that come out. But I would expect there is enough scope to that one day some metal will be found. And there was other thermoelectric applications, particularly these materials. By the way, I did not use the term strongly correlated electrons. They are all called strongly correlated electron systems. And as I already mentioned, semi-exoboride, cerium copper arsenic 2, lithium 6, they exhibit insulating like or semiconducting behavior. If you look at thermal power, they are large. Thermal power is large, thermal conductivity is large, but however, the figure of merit is still not so comfortable. And it is hoped that tuning the material, some of the material will eventually turn out to be a good energy, useful energy related material. Yeah, that's what I want to say. I mean, I'm sure there's enough scope because of the correlations, electron correlations. One day this will lead to many materials, much more exotic applications.
Okay. I have one question.
Yeah.
So when this 4f electron becomes delocalized, what happened to the anisotropy? Basically,
very good question. The point is that all these materials have been studied on single crystal. You see anisotropic behavior of anisotropic hybridization. Since the 4f orbital, I did not use the term crystal field effect.
Yes.
When at high temperature you have fully degenerate orbital, at low temperature under crystal field splitting, the crystal field level has its own orbital shape. Depending on direction of the low field, the low lying state, there are different orientations. You do have a strong anisotropy in all physical properties. So therefore, you have what is called anisotropic. You also have anisotropic hybridization. If you measure on single crystal, the contour temperature measure on the hybridization. Contour temperature can be a directional dependent. Okay, therefore you have also anisotropic hybridization depending upon the orientation of the 4f orbital. This is established.
Can I ask one question?
Yeah, sure.
So in these systems, the origin of skyrmion stabilization, is it bulk driven or interface driven? Why I'm asking this, I'll mention. In ferromagnetic thin film heterostructure, for example, tantalum, cobalt, and boron. In these heterostructures, primarily skyrmion stabilizes because of Jalusinski-Murray interaction coming from the interface.
Correct.
So in these 4f system like samarium based system or cerium based system, what is the exact mechanism?
Okay, I would say that there are triangular. If you look at, I did not show the structure, I did not have time. You have triangular lattices. When you have triangular lattice, when the interside interaction is antiferromagnetic, then you have what is called frustration. I mean, I don't know you can follow, but they're called geometrical frustration. It's not a frustrated due to disorder. When you have geometrical, therefore, you have antiferromagnetic coupled triangular lattice will lead to geometrical frustration. When you have geometrical frustration, by the way, this is, okay, very important. Okay, good that you raise a question. The DMY interaction you normally expect in non-centrosymmetric system. These are all centrosymmetric systems. There is another exotic feature. Thanks for all. The centrosymmetric, that is a paper appeared in science. The Japanese, since there is a centrosymmetric system, how can you have DM interactions in the symmetric system? There is a question, there is an open question. Therefore, how to answer your question straight, there is another open question which nobody knows. But okay, recently there is another preprint. People are questioning the presence of skyrmions in the system. That is some. But anyway, you forget all these things. It is a fact that rare systems do exhibit skyrmion behavior, if not this system, another system. They are found even on single crystals where you have these peripheries or boundaries or zone bounds supposed to be less. It is actually coming from bulk. It is coming from frustration. Within one line.
Thank you very much. I think there is one more question from participants. If you allow, I can.
Sure, no problem. I'm available.
So the question is related to what about dielectric losses in these materials?
They are metallic.
Okay. Yeah.
Nobody one would like to measure. Yeah.
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 I think
I can, okay. Now he's asking, somebody went to that direction. Let me ask the question. Kiran is also co-author of the paper, I think. Yeah, Kiran Singh. And I think thanks to Kiran, we have dielectric setup in TIFR when he was a postdoc. He fabricated, we had a lot of papers. And we have brought up a relationship between dielectric constant and 4F hybridization. I must tell you this. So the 4F hybridization actually is trying to modify the dielectric constant, not in this materials. Other insulating materials onto also the multiporosity. So therefore, it's good that somebody raised a question. Okay, I just want to inform you that the 4F hybridization or delocalization also has an influence on dielectric constant, also on multiporosity. This has come out of our work. We had recently a paper last year on that.
okay. Yes. Thank you very much, sir.
Thank you, sir. Thank you for giving me the opportunity to work in your group at TIFR. So
Okay, yeah,
it was a great pleasure for me to work with you at TIFR.
yeah, you made the setup. We are all using it. So anyway, so
Thanks for giving me the opportunity to make that, sir. Thank you very much.
Yeah. So Kamla Bharti, sir.
sure.
Yes, sir. So if there is no more question, then we can end this session. So we will.
I mean, anybody, I just want to tell you, any of the audience, in case you want to ask some questions, I can send an email, I will answer. And if anybody requires any help by discussion, anytime in the future, in this field, I'll be more than happy to interact without any credit. I don't want any credit. It's only to help my colleagues, other people, young people like you are doing work. I'll be more than happy to get interact and whichever I can contribute. Just don't worry about that. I'll be more than happy to help the people.
Sir. So thank you so much, Professor Sampath Kumaran, for this wonderful talk.
Okay.
So I also thank Dr. Jayavardhan for handling this session. So participants, we have 15 minutes break now. So we will meet again at 3:25. Please log in back by 3:25.
What is the next talk on?
So next talk we have by Professor Sudhagar Chandan from IIT Madras. It is on influence of disorder on the functional properties of 2D MOS2 nanosheets.
I see. Okay. Okay. Can you give me a link? I will let you the
Same link you can
same link. Okay,
join.
fine. Okay, I'll leave it on then.
Yes, sir. Yes,
Yeah,
sir.
yeah. Thanks a lot.
Thank
Okay.
you so much.
Okay.
Thank you very much.
Thanks a lot. Okay. Thanks.